as you remember that we learned earlier was on dynamic balancing. We also done the adjustment. Remember, you have adjustment, meaning that you have to adjust the mass and you have to adjust the position as well as the radius or eccentricity or perhaps the space between plane to plane, and to put that particular parameter on the system so that the system will totally balance. So that's what we have done earlier. Today I'm going to share with you a new topic. It's not a new topic basically. It's basically a subtopics, a new subtopic which call as the force on bearing. If you remember, if I can, we captured what we learned earlier. Yeah, I'm going to share with you the. I'm going to share with you a blank file here. Yeah, I'm going to share with you the working template. The template. This is a blank template, so I'm going to share you this one, and I'm going to write something so that you can remember what we learned last week's. Do you get the new display, the blank slide you have with you? No?
Yes, Doctor.
Okay. Hold on a bit. As I mentioned earlier in the group, we have a technical issue here. Sometimes it works, sometimes. And this one. And this one. Okay, now working. Huh? Okay, let me recapture what we learned earlier in the balancing, yeah? So that you know that where are we basically. So if you remember the last thing that we discussed, we are still talking about the balancing. This one is balancing, this is balancing. Of course, in balancing, there are two parts of balancing. We are going to cover only the first part before we move to the next one. So basically what we done earlier is roto balancing, put it the roto balancing. What you have is a measure, what call it a task, yeah, a measure task talking about adjustment. What we adjust is basically want to put what be the aim, what be the radius of eccentricity, what the position, and perhaps what be the distance. We call it as D. So these are all the parameters that you need to adjust. Parameters you need to adjust. Adjust means that sometimes you have to put, sometimes you don't have to. So need to adjust on the system, so that the system will have totally balance. So this is our aim now. Let me close one of the file here. It's keep interrupting, annoying me. Okay. And the other part, we done this one earlier. I think example number 1, 2, and 3, if I'm not mistaken, sir. And another thing that we're going to look for is forces. Remember forces. And in here, you have a couple of things. First, you need to know what will be the resultant dynamic force. So let's put it the resultant. And on the resultant itself, you will have static and dynamic as usual. You have statics and dynamic. Okay, then you have this one. This is new to you. What we call it total maximum force. Total maximum force. This is new to you. And the other one will be, it's also total, but total, this one maximum vertical forces. Vertical. Of course, when you have maximum, you have another one, minimum, right? Vertical forces. Okay, so in here, our concern is the forces, yeah. Our concern is this one. Our concern is what? Our concern, yeah, is to look for forces on bearing. Remember that, because it is very logic if I'm saying that the shaft will be the shaft will be supported by bearing. So we are going to look for what are the force, how much force exerted on the bearing. So all are concerned on the bearing. Okay, so whatever you have here, static, dynamic, total, maximum force, total, maximum vertical force are all on bearing. Okay, so you can turn to page 101 in your books. You have a introduction, or perhaps the what do you call it, the the theory talking about all the forces. So let me begin with a very simple one. So what is the dynamic force on bearing? So what is the dynamic force on bearing? Sometimes we call it in bearing, sometimes call bearing, doesn't matter, because we are not talking about the grammars here. So on bearing, look at the on bearings, because we have so many bearings, on bearing. So what is the dynamic force? So first, let us define what is the dynamic force. The dynamic force is basically any force that make your equation mr omega square. So that is the dynamic force. On bearing mean that this one on bearing mean that is the resultant. Sorry, it's not resultant. It's the effect of uh of force, of applied force. Put it applied force. Applied is the effect. Remember, we learned this one in gyroscopics. So let us now make a very simple assumption. For example, so let us now you have, okay, this one you have a shaft, this one is a bearing, as I mentioned earlier, and then you have a unbalanced mass. If you allow the system to be running with constant speed here, let's say this is a bearing of A and B. So if your eye is here, for example, so you are looking at this one, correct? And rotating by the omega. And every time you rotate and you try to pause it, because you want to make analysis. Okay, so what you have, you pause a bit, for example, that you pause while it in certain position. Okay, you pause in certain position, then you make analysis. Pause in certain position with omega, of course. You know that as you're creating the free body diagram, you will have a force. You will have a force of this one. Okay, this one here. You will have force is here. If this one is the FC, if this one is Fn, remember the normal and also the centrifugal force, or sometimes we call centripetal. This one is Ft. And due to the angular velocity is constant, so this is no concern of our analysis. So what you have now is Fc is equal to Fn is equal to mr omega square. Okay. So what is the FCM? This one is basically dynamic force. And also we call it what? We also call it as a what? As the unbalanced force. It's a dynamic force, but the unbalanced force. Unbalanced force. It's a dynamic force, but unbalanced force. So in conclusion, when I say dynamic force, it can be representing to you that it is unbalanced force. It can also be that unbalanced force, force on shaft can also be here force on bearing. So these are all the force that we are going to look for on bearing. And these are all dynamic force. So when I'm saying dynamic force, so you have to understand that dynamic force can representing force the unbalanced force creating by the unbalanced mass. This one is unbalanced mass, right? This is unbalanced mass. So it will give you unbalanced force. Then force on shaft because it's supported by shaft. Then you have a force on bearing. Okay, this is the introduction before we go further. Okay, so as you understand that one, so allow me to to go a bit deeper when you have so many force, for example, and the system is supported by bearing. This one A, this one is B. Let's see, this one is X, this one is Y. Then you put omega and let omega be constant. Okay. So what we learned earlier on adjustment, yeah. So on adjustment, on at AD adjustment, we learned that okay, this thing will be rotating and will be creating this one. Be creating one M R because this is R A omega square. Same thing here. It will be rotating. This one is M for B This one is omega square. This one is R A R B. This one on adjustment, yeah. So typically on adjustment, put or add what mass. This mass is the balance mass. Balance mass. Add x and y. This is what we learned earlier. Before I go to the next one, yeah. So you are saying that okay, I'm going to do this one. There's no calculation here, just theory, yeah. So this one, same, same shaft, identical. This one is bearing, of course, and this one is force. Again, same thing. This one is put it A, put it B. This one, the creation of the unbalanced force, of course, here will be pointing outward. This one, yeah. Let's put it here as M A omega square. Do we have a square up here? Yes, square, yeah. And you have here same thing. This one is M R for B, also omega square. So if you want to apply this one, to comply this one, what you have to do is you put mass here, because it mentioned about where the position is X and Y. So put mass here, and we put mass here. Because this is not concerned about bearing yet, yeah. So you will have this one is M R for the unbalanced just now, to balance omega square, but this one is at where? And X at X. This one put it here, M at Y is unbalanced. This one to omega square. So now the system is so many L, totally balanced. Agree with me or not? This is what you done. This one done. Agree with me or not? Yes or no? Okay, thank you, Lee. Now, today, we don't want to talk about adjustment. Now, go further for forces. Go further for forces. So, the equation is now, what is the dynamic force? Dynamic force, yeah. Remember, I'm talking about dynamic force now. On bearing. Remember, on bearing. We have dynamic force on three kind of dynamic force, right? What are the dynamic force? As I mentioned earlier, unbalanced is also dynamic force, bearing also dynamic force, and the other one is shaft. So on bearing now. Okay, put the same issue now, or the same what do you call it? The same problem. I want you really understand this one. So the next thing will be very easy for you, yeah. So you have a mass here just now, the unbalanced one. This one also the unbalanced, isn't it? With this one is you create just now this M. If this is A, yeah, and this is B, yeah, this is X and this is Y. You create just now is M R for A. This one omega square. The other one is another one is the M R for B, omega square. And we don't want to put mass now. We are going to what? We are going to look for forces. Dynamic forces, of course. Dynamic force. So how is it? It's not very difficult. It is exactly the same thing. Same thing. You also have a mass earlier, but now that mass, the unbalanced mass here, does not exist. We don't want this. What your concern now is? What is your concern now is what? Is to give force, or to take, or to take force, or to give force. So I'm going to draw with another color here so that you can differentiate. This one here. This one is force. So what will be the magnitude for the force? This M is an X omega square. Same thing here. This one is M Y omega square. Okay, we do not know what is the MRX and also MRY yet, because we have to do some analysis. This is the theory, what it did dynamic force on bearing. So this is what this is known. Okay, this one, let's put it here. This one is dynamic force, correct? It's a dynamic force. Remember, any parameter mr multiplied by omega square is a dynamic force. But the dynamic force is now come from, dynamic force is from the unbalanced mass. Unbalanced mass. This is also dynamic force. Am I correct? But this dynamic force is not from coming from the unbalanced mass. It's basically the balanced mass, which we call dynamic force on shaft. Okay, but our concern now is what? Is to look what is the dynamic force on bearing. So on bearing, remember, shaft and bearing is always opposite direction. So you have another force acting oppositely. This one. The green color is okay with you, class, or I might change another very dark color. Let's put it there, brown there. Yes, more. Okay, so now the magnitude is exactly the same. You have the magnitude of mr x omega square. You also have this magnitude of mr y omega square, but yet this one what we call as dynamic force on bearing. You understand me or not, class? Understand me now? Is that clear? Anyone?
Yes,
Hello?
doctor.
Okay, remember, yeah, it's always, you always shaft and bearing is always opposite. Shaft and bearing opposites. Later on, I'm going to explain in the practical, always opposites, or always shaft and bearing always opposites. Okay, so this is, remember we have number one just now, dynamic force on bearing. Okay, number two, you have resultant force, also on bearing, also on bearing. Everyone very clear about resultant. When we are talking resultant, is basically in engineering perspective, yeah, is basically the resultant here. Okay, the resultant of some total, yeah, for bearing A, for example, yeah, is equal to the force bearing A plus this one bearing A. This one is where you found that this FA coming from dynamics, the FA coming from statics. So this one is not a big deal. We're done earlier, isn't it? So we're going to look for FA. So when you're talking about static force, remember this one. Okay, let me put another equation. F, this one for B, you will have FB plus RB. Of course, yeah, this one all vectors. Don't forget that, all vectors. It is not, you cannot add up together as normal procedure of addition. You must be in vectors, because we are still dealing in vectors now, or dealing about vector. So for static force, for static force, it's not force, it's not for static force, for static force. Remember, even you're talking about static, still on bearing. This one, on bearing. Because from the very beginning, we are talking about what will be the force on bearing. So static force on bearing. So the equation must be coming from, or the definition will be coming from free body diagram. And this is nothing new to you, yeah? And you are applying equation of summation of moment about about whatever equal to 0 is the equilibrium equation. The other one is summation of force equal to 0. So this is the equilibrium equation, equation. Okay, so how is it, how is the free body diagram? So look at here. So this is the free body diagram. Free body diagram. How is it? You have exactly as what we have earlier just now. This one and this one. This one bearing, yeah. This one you have, okay, put it here. The mass. This one is the mg4a. This one is the mg4b, and this is the x and y. So you will have here x, you will have here y. Okay. Or if you want to put A and B, doesn't matter. So as long as you know that this is R pointing upward, this B will be pointing upward. So this one and also this one is basically your assumption. This is our assumption. Our assumption. We are assuming that it is pointing upward. Can we assume it pointing downward? Yes. You can also assume that it is pointing downward. It doesn't matter. So now, then you start using the equation summation of moment just now about x, for example, is equal to 0 for the equilibrium condition. So you have then this one, point A and point B, correct? So you will have, okay, let's assume boundary condition, anything rotating, clockwise from your seat will have positive notation. So you have the mg for A multiplied by ax, correct? You will have what? Another one, you will have excuse me, you have minus by plus by mb mb mg for b. This is the a bx minus by the ry multiplied by a xy. One equation, isn't it? So this is the moment. So you have another one, force summation of f equal to 0. So seeing that anything that pointing upward as positive, you will be getting here as x plus ry is equal to ma for a plus mg for b. So you solve this one. Finally, when you solve this one, solve and get what? You get Rx and Ry. Okay, supposingly, let's say, supposing, because we don't have magnitude here. Supposingly, when you calculating, you found that the Rx equal to something, and it is positive here, positive. So it means that pointing upward, correct? And supposing you calculate, you have Ry here, and it's also positive here, and also that whatever you assume is basically correct. Okay, you understand me or not, class? This is our assumption saying that, okay, any result or any magnitude by ry and rx, you calculating, then you find that both are give you positive, so your assumption is correct. So and this one, remember this one is what? On what? On sharp. This one is on what? I cannot put so many arrow, then you make you confused. Just I put it here, right here, very close to the arrow. So this one on sharp. This one is also on sharp. What is our concern just now? Is on bearing. So you have to inverse the direction. So I'm going to inverse the direction. This one inverse direction, bearing. Inverse direction, bearing. So this is exactly as what we've done in gyroscopics. Understand me, class? Hello?
Yes, doctor.
Okay, now. So then you make the resultant. I remember resultant. Remember, resultant is on all on bearing. So let's say resultant force on bearing A, for example. Okay, bearing A. So you know that you can construct a polygon. So you can construct a free body diagram, or if you don't want, it doesn't matter because you already completed the whole exercise of calculation. So you pick up one here. Yes, now where are you? This one, you take this one as the resultant. One be pointing upward, the other one be pointing downwards. Okay, so that is the resultant. This one will be discussed further in example. Because we don't have a magnitude, it's very sorry, we don't have a numerical or magnitude, very difficult for me to explain. As long as you understand what is the resultant force is good enough. Number 4 here, this one is new to you. Number 4 could be number 3. Number 4 is the what did I see just now? Is the total force but the total is not total force. So it's total maximum force. Total maximum. We have total maximum force on bearing. Doesn't matter which bearing you refer to. So as long as you're talking about total maximum force, so the total maximum force here is supposingly on bearing A, for example. So you will have FA, you also have RA, sorry, and this one is all vectors. All vectors. So this one, remember this one. Follow, always follow, always follow the static force. Okay, for example, okay, this one vector. For example, so you know that the static force is pointing downward just now, isn't it? The static force pointing downward. This one is RA, for example. And again, this one is pointing upward. This one for shaft, remember? This one for bearing, remember? This one bearing. Okay. At the same time, when you construct the polygon, you found that the FA will be pointing here. FA be pointing here. This one is your FA. FA. This one is dynamic. Sorry, it's not dynamic. Typically, it is a dynamic. I'm going to say that it's on bearing. This one bearing. So of course, on shaft, it will be not pointing at that point. Be pointing the other way around, isn't it? Be pointing the other way around. So here, opposite direction. This one is FA, correct? But on shaft. So our concern is, remember, on bearing, So the shaft one is not our concern. But anyway, in conclusion, you have to read the equation very, very careful, because if you're designing the shaft, you are also need to concern about the shaft. If you are designing the bearing, so you need to know what the bearing is, or you need to know what are the force on bearing. So it basically refers to the equation. Refer to equation. Sorry, it's not refer to equation. Refer to equation. Refer to equation. So what I'm saying here, always follow the static force, because the static force is always on vertical. Remember this one. Static force always vertical. Vertical pointing outward or vertical pointing downward. This one is vertical pointing downward because the shaft is pointing upward. So bearing will be pointing downward. So when I say the total force, so you take this one, it will rotate here, jump. Then this will prolong a bit. So you add up as normal procedure of addition. You get me? So let's say this one is 100. Let's 100 Newton. Let's say this one is 200 Newton, for example. So your summation of F for total is basically 300 Newton. You add up as usual, as normal procedure of the addition. Same thing for bearing B. Just remember, always follow static force. The static force must be on bearing, always follow static force. If the static force fall on the upper side, so you bring this one upper side. How this one occurs, I will explain further. Will be explained further when we have the example later on. So the other one is, what is the other one? The other one is total. Last one, maximum or minimum vertical force. Vertical force. Total, maximum or minimum vertical force. How is it? Let's figure out the same thing here. So I'm going to put it here. FA. Put it here just now, FA. This one on bearing. On bearing. E, for example. So remember this one, total maximum or minimum vertical force is the product of forces, in vector, remember, in vector, by resolving the dynamic force, the FA, put it there, the FA, by resolving the FA in vertical and horizontal axis. Okay, so what does he say? So now, if this one supposing theta, you know the theta is later on. So the theory say that it is the resolving of the FA in vertical and horizontal. So you resolve this one, you'll be getting FA sine or cos here. Sine or cos here. Sine theta. You resolving this one, you'll be getting F cos theta. Am I correct or not? Correct or not? Correct or not?
Yes, doctor.
So when you resolve, what does it mean? So when you resolve, so therefore, the summation of F maximum for bearing A, for example, is equal to, and saying that anything that pointing downward as positive is equal to, you will have, of course, this one will be in brackets. You will have F of A plus FA cos theta. Okay, of course, we have another one for B. Then you check where will be the maximum and minimum for A and B. Okay, what happened to this one? What happened to this one? I will be talking this one later on. So what happened? What happened to the horizontal force will be discussed in the example, because I don't have magnitude. So it is, it's not very clear if I can explain here. I don't want to explain with so many sentences and words. I'm going to explain when you have the examples that make you more, understand. Okay, so that is the completion of theory of today regarding the forces. Any question before we move to the examples? You have the example on page 102 with solution. Any question? No, if there's no question, I'm going to go back to the theory here. You have this one. Okay, so look at the next one, example. So from example, then you understand. You can understand fully how to basically, what do you call it, solve, or how to go about it. This example is taken from last years in the exam. Typically, this type of question will be in the exam. If you have so many, sub question will be in the exam. Typically in test, it will stop at here. In test, typically, it will stop at what will be the maximum force here. The next one is for the exam. Here and here for tests. Because it takes longer times to solve every component of the equation. Okay, let's assume you have what you have here. You can turn to page 102, your solution. I'm going to explain based on what you have in your hand. Yeah. Okay, now figure shows shaft 1.8 meter. This one, yeah, 0.6, 0.3, 0.9 will give you, add up together, will give you 1.8 meter with two bearing A and B. Two bearing A and B here. Then carry two masses C and D. They provide you the masses is 7.5 and 10 kg respectively for C and D. The masses are rigidly attached to shaft, fine. And the radius of rotation, sometimes we call radius of eccentricity, it is basically the same. It's 775 millimeter and also 50 millimeter from the axis of rotation. From the axis mean that if your eye is here, you look at one point, side view, this one the front view, this one is side view. You find that for the C here is 75 millimeter. For the D here is a 50 millimeter. And the position between C and D is 60 degrees to provide you as the position. If the shaft rotates constantly with the speed 120 rpm, determine the dynamic force on bearing A and B. Dynamic force on bearing A and B. The total force is also dynamic force. The total force of bearing A and B, the maximum total force on bearing A and B, the maximum and minimum vertical forces on bearing A and B. I already explained this on what are the force on the bearing. Is basically the opposite direction of the force on shaft. Okay. Okay, now we move to the next one. I'm going to, if you want to solve this one by graphical, for example, sorry, by analytical, for example, you can, you can check my latest edition with the analytical. What you have in your hand is basically all in graphics. Yeah. Okay, let me explain with graphics. Yeah. So now, so in graphical, when you came to solve with graphical, so of course you need to tabulate tables, and this is compulsory. Tabulating table for graphical method is compulsory. So table must, yeah, table is a must to construct table. Okay, now plane. Plane is basically refer to your plane here. You have A, B, C, and D as usual. Sorry, A, C, D, and B. So you have A, B, C, and doesn't matter this one. Yeah, this one doesn't matter. It's up to you. Then you have this one. Put it all the parameter A and B. There is no mass for bearing. There's no radius for bearing. But typically in practical, the bearing has a mass and also radius. But it is not our concern to weight what will be the mass and to consider what is the radius of the bearing. But if you're talking about designing a bearing, for example, in some purposes, yeah, you need to know what be the radius because you want to fit in the shaft in the bearing. So in here we are not. This is now our concern. Our concern now is to look what forces on bearing only. It is not to design the bearing by the dimension. We are going to design bearing to what, to that extent of force on bearing. Okay. When you do the design later on in your later year of your study, you need to know what will be the radius. Of course, math you don't bother. You need to know what will be the radius because you will have to design the shaft because the shaft will be fit in well in the bearing. Then you have to design all the keyways and so forth to ensure or to lock the bearing and also the shaft. Here, I'm not going to talk about that one. I'm going to talk only what are the force on bearing now because our concern now to look for the force. So there is no mass here, there is no radius. But in fact, you have this one and this one, what? This one representing force on A. This one representing force on B. If you multiply with omega square, because the omega square is basically constant parameter. So that is why if you look books, many books, they provide this one with omega square. But remember that when you put this for omega square, this number will become so huge, isn't it? This number becomes so huge because omega square, let's say the omega 1000 RPM. Omega square is 2 pi 1060. You square it, you have a very huge number. So I'm not going to put omega because the omega constant. So I'm going to put omega the end of my calculation. Okay. Just remember that this one presenting FE and FB. So C, they provide you C, M and radius. They provide you D, M and radius. You have this one. Okay, now you have to look for reference. Remember, so you have two. You have two possibility to check on reference. One will be A and one will be B. What is the reference? The reference will be any plane with an unknown parameter. So we have the B unknown, also A unknown. Here, I'm selecting A to be my reference. Okay, so as I decided to select A as reference, what does this mean? Yeah, it simply means that every mass will be referred to A. So that is the concern now. Every mass will be referred to A. So what this mean? So A now become reference. So you measure from A, you measure from A, you measure here from A, and as this one only one-sided, you have the all positive. Look at A. B is 1.8, 0.6, 0.9. Then you start, multiply the numbers here. You have this one 1.8, 3%.5, and 450. The position, we do not know what is the theta A because they don't provide what they provide. This one is 60. This 60 is basically one from C to D. Put it there, 60 to D. And they also provide you this position. Okay, the position. Okay. So that is how to construct. The next thing will be constructing a polygon. Okay, as I mentioned earlier in my first lecture, the creation or the construction of a polygon exactly as what we did earlier. The only difference now, you have another plane, which is plane on bearing. So now let's see now. Okay, I'm going to construct this MR versus theta as we have only one unknown. So this one MR versus theta. This is my boundary condition saying that the MRD must be equal to 0, because you know that you are going to balance the system, so you need closed polygons. Okay, now, so you have, okay, 337.5, 0 degrees. Okay, the 0 degrees is fall are pointing upwards, so pointing upward. 337.5 pointing upwards, up, pointing upward. Let me then you have what? You have 450, 60 measured from the reference. So measured from reference 60, this one look at here, clockwise from your seat. So it's 60 degrees. You will have here. And you know that this one only you have 2 lines. You complete the polygon, you make it 3 lines. So it's easy. You can solve by using analytical, by applying sine rule and also cosine rule. Or if you construct a polygon, you measure the last line. As measuring the last line here, you measure here, then you equate with what you have here. Here, look at here. I'm measuring and equating from the table. I'll be getting this one, 380 kilogram millimeter. And this is the MR. It's not the mass, yeah? This is the MR. Okay, this is the MR. So this is not our concern basically. Our concern is what? To look for FB. And your FB is MRB omega square. MR calculated, omega given, you'll be getting as such. You'll be getting 60 Newton. Is it not? So what is the position? So let me ask you. So if you calculating this one, yeah, this one, you get this one 60 Newton. This is 60 Newton. So this 60 Newton, this 60 Newton here, yeah, here, isn't it? On shaft or on bearing? From the polygon, on shaft or on bearing? On shaft or on bearing class? Anyone? On shaft. Thank you, Tan. It is on shaft. Remember, whatever you done here, because you know the system will be supported by the unbalanced mass just now is fitted or rigidly fitted on the shaft. This is on shaft. Our concern is to look for on bearing. This is something else, isn't it? So on bearing. So allow me to put it here. So you have what? You have AB. So I'm going to draw a last line here. This one on bearing, on bearing what? On bearing B. Okay, on bearing B. Yeah, on bearing B. I'm going to construct the last line. Only the last line. The last line is pointing downward. This one. This is the FB equal to 60 Newton. As Tan say and agree that this one is on shaft. Our concern now is on bearing. So you have to inverse the arrow. You have to inverse the arrow. I'm going to put it opposite direction. This one. Same magnitude. Remember, this one is F also 60 Newton. But now on bearing. If you like, you can put palm here to not to differentiate which is the shaft and which is the bearing. So this one. So if you calculating or if you measuring the last line of the shaft, yeah, this one, remember this one 0, they provide you what you've been given. You have 215, isn't it? Correct? You put it here 215 from the vertical. This one is 215. 215. This one is 180. So 215 minus 180, you'll be getting what? What do you have for 215 minus by 118? 180. Sorry, 180. What do you have? 35. Correct. Thank you. 35. So where is your 35? So yeah, my computer is running out of battery. Hold on, class. What is the 35? This one is 35, and this one will be 55. So that is why in your result you have this 155. Okay, so let me clear about this one. Listen up very careful. Listen up very careful, class. This one on or it's not on, yeah. This one, the position, yeah. This one in table, put it in table here. This one, no. This one for further calculation. This one will not be a part of your table. Remember that. This one is in table. This one for further calculation. Okay. So here, okay, student might ask me which one is correct, the 55 or the 35. It doesn't matter. If you put 55, you put it. Sorry, if you put 55, you put it here. 35. This one is FB 60 Newton. It's also correct. If you want to put the other way, as what you have in your solution in your book, you can put this one the other way. FB equal to 60 Newton, 55. So it doesn't matter which to which. Okay, as long as they must be what? Magnitude and direction or position. Okay, complete first parts. Any question? Any question? No? Okay, thank you. So the next thing will be calculating the B, forces on bearing, of course. Yeah. So the completion of the table now will be here. So this one you can 215, put it here 215. This one 0, this one 60. Then you have only one unknown. This one is already completed, so you move to MR versus theta. So you have this one, MR versus theta. And this is your boundary condition. Boundary condition. What does it say? Whatever you construct the polygon, if the polygon is not closed, you have to force yourself to close the polygon because your aim is to balance the system. Okay? Then when I construct the polygon, and again, as I mentioned earlier, if you go back and construct this one, with scale, we'll not be getting as such. We'll not be getting the same polygon because this one is constructed by freehand polygon. So you start with 5, 6, 2.5, 0 degrees. So 0 degrees pointing upward. So I bring up here is pointing upwards. 5, 6, 2.5. The other one is 560 degrees. 60 degrees of the vertical. You have this one. The next one you have 215 just now, measured also from the vertical 215. Then it will fall here. And it is not closed polygon. Isn't it? Then you force yourself to close the polygon. So this is the last line that you measure. You cannot calculate this one. You have to measure this one. You have to construct this one, yeah, in scale, of course. This one, and you equate from what the thing that not completed in your table. So you have this one, and it will bring you equal to MRA. Then multiply by omega square, you'll be getting 86 Newton. Again, this one along the line, this one is the on shaft. It is not our concern. It's not our concern because the question doesn't tell us or the question doesn't ask us to look for the force on shaft. So what you need to do now is go back here and look for bearing A. So I'm going to construct the last line. You have the last line here. Okay, the last line will be here, pointing downward. This one is FA equal to 86 Newton. You agree with me if I'm saying this one is on shaft. And again, this is not our aims or our objective. This one be our. This one is the FA also, 86 Newton. It's pointing the other way around. And it been measured here. You measured earlier just now. It fall at 204 degrees. 204 degrees. Isn't it? Just now 215. The next one is 204. Here, 204 degrees, the last line. So you have 204. Then you want to look what will be the position. You need to know what will be the position, right? So you have 204 minus by 180. What do we have? Equal to what do you have for 204 minus 180? Anyone? Is 20. Anyone? Is 24 degrees. Yes or no? Yes or no? 24. So where is the 24? This one will be 24. This one will be 66. This one is on bearing. This one will be in table. Put it in table. This one will be used in further calculation. Of course, in the test or exam, you don't have to do this one. This one is only part of your notes. Okay. Otherwise, your work or your solution will be very, very messy. Okay. Any question? No. Okay. No. Thank you. So I'm going to then you have this one. Again, this one in table. This one next calculation. Okay. Move on. The question keep asking us about what? The next one is we covered this one for dynamic force. We want to look for total force. Total force is basically whatever you have for the dynamic force, and we add up together with the vector due to the static. So we come back here, we go back here, and then you look at the static. So as statics, I'm not going to do this one in detail because you are very well versed in static. You've done this one in static. The resulting the forces resultant in static as well in dynamics. So this one is static. First you create or you construct the free body diagram as usual. This one and this one. This is your assumption. This is your assumption on bearing A and B, for example. Then apply on a moment or couple with the forces. You'll be getting this one positive here on shaft. This one also on shaft A and B. Again, this is not our concern because our concern is bearing A and B. So you have to inverse the direction. Only inverse, you take the same magnitude but invert the direction. Now it's no longer pointing upward, we're pointing downward, be pointing downward. Okay, now it's on bearing. This one is bearing. This one also bearing. Okay, then you add up together. Of course, you add up together with in vectors. The next question, we go back to the question first, is to look at what is the total force. So total force, you have to look for static and dynamic. So we select or you collect static and dynamic as well. Okay, yeah, total force on bearing A. Okay, this one is what you've done earlier, facing of pointing downward, and this one is also dynamics. This one is dynamic. Then you add up together in vectors, of course. You can use parallelogram. Excuse me. You can use parallelogram theorem, or you might be using analytical by using cosine rule. All calculations are well shown in your books. So finally you'll be getting as such, and you have the position, of course. This one is done by parallel. This one parallel. Parallelogram theorem. This one is by cosine rule. Same thing for B. This one pointing downward on bearing. Just now here is also on bearing. So you add up together the product of vector. You will give you as this one and this one. I'm not going to this one in detail because this one is nothing new to you. Okay. Any question on total force before I go further? Any question? Hello?
No, doctor.
Okay, now this one clear, yeah? So I'm going to move this one. This one is something new to you, so I'm going to focus this one. Very detailed. Okay, the next question is total maximum force. Total maximum force. Okay, now. I did mention just now when you're dealing with total maximum force, what does it mean? It simply means that you bring the dynamic follow static. Remember the keyword only. Dynamic follow static. You have this one in your note. You can look in your notes, yeah. If this one is very small, you can look in notes, yeah. So I now make it bigger so that you can see. Okay. What you have here initially, you don't have this one. You don't have this one yet. Correct. What you have is these two line only. This line, and this one. Am I correct or not? Isn't it? I did mention just now. You bring the dynamic, and it will fall at statics. And as you all know that the static will always in vertical. Sometime a vertical pointing upward, sometime a vertical pointing downward, depending on your solution of the free body diagram. Supposing it is pointing downward, so you add up this one as normal addition. Add up 98.1 and 86 as normal position. You'll be getting this one. We do not know this one is maximum or minimum yet because you have another one. But this one is maximum for A. Okay, now I will explain this one how the in practical. Yeah. Any question before I move to the next one? Any question? So as you bring the dynamic follow static, then only this one you will have. Supposingly, it is not as what you have here. Supposingly, you have, okay, supposingly, you have this one. This is your dynamics, Fe. Let's see Fe equal to 100 Newton. Your Re is pointing upward. Re is equal to 50 Newton. Okay, you follow this one. Or you can also, you can also do the other way around. Doesn't matter. You can also do this one. Doesn't matter. As long as must be fall at. So it will fall here, a bit long here, then here. So your result will be what? 150. So it's always following static. Remember, it's always following static. A static will fall on verticals. It doesn't matter pointing downward, pointing upward. Is that clear, class? Okay, let me finish one. Then I explain why we are dealing with this one. Okay, now yeah. Okay, we have this one again just now. This one you don't have yet. You have this one is correct, calculated from the polygon. This one, yes, correct, from the free body diagram. Then you bring this one and it will fall as statics. You add up together, then this one is no longer exists. So you add up together, So you'll be getting 1336 Newton. This is maximum for bearing A and total maximum force on bearing A and B. Okay. Okay, now, so now how to explain this one? Okay, listen up very careful this one. Because in exam, sometimes you ask you explain the total force. Remember in the exam, they're asking about CTPS, critical thinking problem solving. Yeah. Okay, now listen up very careful. You have to remember that the rotor is keep on and on rotating, isn't it? It's continuously rotating. Am I correct or not? Okay. When you look at one point here, when the equations tell us that, okay, calculate what happened to the structure, when the position of C and D at that particular instant. This one, what does this mean? Yeah, it means that you pause a bit, then it will stay as it is. Because as you cannot do the analysis when this thing will keep rotating. You know, you get what I mean? So this one, you pause a bit the position, then it will stay as one. And this one will keep rotating with the omega here. Correct? Yes or no? Yes or no? It
Yes,
could
sir.
be. It could be pointing that way. It could be pointing that way, isn't it? This one still 60 degrees. This one will be C, this one will be D. Am I correct or not? But the question asks you to define what will be the force during that position. So you pause a bit, it will be at that position. So that is why when you calculate, you will be getting the result of this one at that particular instant. If this one will keep changing the position, for example, if you're pointing downward, you'll be getting the same magnitude. Yes, it is, I agree, but you'll be getting different position. Okay, now let's go back to this one. Okay, you understand the one, then we go back to this one. And the static will not will not affect anything, because what is the static force? The static force is simply that when you off the engine or you off the motor, you off the source, it will be carrying the static force only due to it. That is why it's always pointing downward. It's always pointing downward. Okay, now, so now let's go back to this one. Okay, that when you understand this one, then Okay, at that particular instant, you calculated that this this FA is here. This one is here, and this one is always pointing downward. This one make noise. Not noise. Make sound. This is not noise. Make sound. Make sound. SOUND. How is it? Okay, listen very careful. Don't laugh, yeah. Listen very careful. So when you on the engine or motor or whatever, it will sound like. Am I correct or not? Can you hear me? My voice humming. Yes or no? So what does it mean? It simply mean that when you off the motor, it will be that point. This one is humming. 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 Humming sound. Okay, humming sound. Okay, this one. Then when we meet the static, what happened? When it meets static, it become. Okay, so when we mix static, it will jump up. It will jump up a bit. So this one is due to what? Due to maximum. You understand me now? When you hear, how can you hear? You cannot hear by without using devices. You need to hear as you know. At least you use a stroboscope like the doctor aware. This one, right? If you want to look the very careful, the actual one, you have to use what they call is sound level meter, or perhaps by using vibration analyzer. So it'll be giving you spectrum, SPE, spec DRUM, spectrum, such like this one. Okay, if you don't trust me, okay, you go to the any laboratory, you look at the system is not balanced, so it will run when the system is running. So it is totally balanced. When the system running, so that one is not balanced. Okay, okay. Same thing like this one. Same thing like this one. So this one you can measure. You can also hear by using devices, of course. Okay, this one is the true in practical, but not this one. This one is not true in practical. This one is only analytical. The maximum and minimum vertical forces on bearing. You understand me, class? For the first part, this one. If the exam question asks you explain how this maximum total force be A and B, then you know. But don't put it humming. No, yeah, you have to put it sound. Now this graph. Put it this graph. One is the humming constantly. The other one you have pitching. This one pitching. PITCHING. Pitching up. Okay, look at this one now. The last one before we move to the next example. So the maximum minimum vertical force is simply mean that same thing here. So this one you calculated earlier from the polygon, this one from the free body diagram, and of course this one all on bearing. Then you resolve. Remember I did mention just now the minimum and maximum vertical force. If resolving the dynamics into x and y, so this one is x, this one is y. Then you add up together in vertical. You add up this one and this one. Of course, the product will be in vectors. So you add up together. It doesn't matter when you are saying this one pointing downward, pointing upward, positive, doesn't matter. It's up to you. Supposingly, supposingly you are saying that okay, I'm not going to follow the solution. I'm going to do my own solution. Doesn't matter. Now let's assume you pointing downward as positive. What you have here is excuse me. You have summation of f is equal to this one will be negative 98.1, isn't it? This one will be plus, you'll be getting this one, 86 sine 66, correct? You'll be getting here, you check correct or not, you'll be getting 19.54 negative, and we do not know yet whether it's minimum or maximum yet. You'll be getting as such. What does it mean? Is equal to 19.54 pointing downward, correct? Because this negative is not the integers. This negative telling you about the position and representing the vector. You go back in this one, same thing. You have this one. This one you resolve into x and y. Then you add up together in vectors for the statics. You be getting a supposing you are going to use another boundary condition saying that any force pointing upward is positive. So you'll be getting it as summation of force is equal to this one, yeah. This one is 73.6 plus this one is 66 sine 55 equal to, you be getting the same result, 24.45 negative and equal to 24.45 pointing downward. It's still maximum, still minimum, doesn't matter where will be your boundary condition. But of course, you have to make the boundary condition same for both. Don't do the other one pointing the upward, the other one pointing down. It is not correct. You have to pick up or select any one boundary condition for both. Okay. Okay. Now, my question is, I'm going to ask you this one. So you have this one in vertical. Sorry, you have this one in vertical. Then you have this one, correct. What happened to the horizontal? What happened to the horizontal? This one. Any question? It's not any question. Anything, any response. What happened? What happened? To what happened to this? Anyone? Anyone? Okay, if you don't, if you keep quiet, I'm going to leave it like that, and you have to check or you have to seek the answer on your own. I would like you to respond whether it's not correct. Doesn't matter as long as you respond, meaning that you are with me. Otherwise, I don't know whether you fall asleep or not. Because you are the other side, which very hard to me to detect whether you are with me or you are not. You are not understand or not. Yeah. So yes, who's on the line?
Lin.
Yes, Lin.
Is
Any
because
motion? What do you think, Lin?
is because it is horizontal, so we don't calculate it. We do not.
What? Okay, you as an engineer now, why you don't calculate this one? What happened to this? The horizontal force. This is we call as axial force. This one is the principal force, is the vertical force. Sometimes we don't call it vertical force, yeah. We call it the principal. Sorry, we don't call it vertical force. We call it principal force. This one is axial force. Why? Any other question? Sorry, any other response?
Uh, it will be cancelled out by the rotating force.
We cancel rotating force. We can look at this way. This one pointing to our right hand side. This one also pointing our head right hand side. It's so no, it is not. It's not correct. If you answer that one, I give you only 1 or 2 marks out of 10. At least you answer. At least you keen to answer. So as this one, yeah, the fx and f, this one also fbx, yeah. So these are basically the axial force, and the axial force is basically very small. Very small, yeah, very small. So we cannot ignore the axial force. That is why in designing the bearing, you have to look for axial force. You have to calculate this one, yes, but you have the SKF, handbooks to look at what will be the axial force, because you have the principal force and the axial force. So most of the axial force will be absorbed by the bearing. So that is why bearing also worn off, because if you don't have the axial force, everything will perfect. So the bearing will not worn off or not fails. So that due to this one, the bearing force will be also acting. Sorry, the axial force acting on bearing. So it gives some problem on bearing. But of course, the bearing also have the intention to basically cover all the axial force. So in engineering purposes, when you're designing the force, if you call out the vendor, so the vendor will talk to you what be the principal force, what be the axial force. Then we'll check on the handbooks. But as an engineer, you know that the axial force is very small, and it will be what? It will be absorbed by the bearing itself, by the bearing itself. Okay, so that's about it. I think that is covered the the topics. So if you move to the next one, yeah, if I can share with you, a bit before we, I would like to basically solve a couple of questions before we move to the next topic. But before that, I would like to also show you example in your notes or in your books. This one, yeah. If you look at the next example, example number 5, you have both method. One will be the method for the analytical, the other one is for graphicals. This one we covered. Look at this one. So balancing just now, we covered adjustment, alhamdulillah. Then we covered force. Yeah, we covered force. So this one for so many force after we covered. So the last one here is, remember, is speed limitation. Limitation. Speed limitation. Or sometimes maximum speed. Maximum speed. What is this? What is the maximum speed? Look at here. So if the question asks you to define what is the maximum speed, don't worry about that one. So you know that the F is always m of omega square. If you want to look force, if the question asks to find force, so the omega must be given, correct? Of course, the m are coming from polygon or analytical, correct? But now for speed limitation, or sometimes we call maximum speed, again we use this one, F equal to m of omega square. So this one unknown. Go back this one just now. This one known or given. This one calculated. This one, you find that one. Correct? Here, this one unknown. This one calculated. You have to calculate. And this one must be given. Must be. Okay, they must provide you this one. Typically, they provide you in terms of Newton, sometimes in Newton of stress, it doesn't matter. So they must be provide this one. So you will have the omega. Of course, yeah, if you have two bearing, for example, you'll be getting FA, you'll be getting A, this one also A, you'll be getting omega A something. And the other bearing, same thing. FB equal to B, omega B, you'll be getting omega B something. Let's see this one radian per second, this one radian per second. Do conversion, you have the NA equal to RPM. Do conversion, you have the NB equal to RPM. For example, yeah, I'm assuming, for example, here, let's say that you have here 1,500. This one is 1,800. Then you have to what? You have to decide this side now. This side, DECID, decide now what is the maximum speeds of the system. A, NA, or NB. And now you tell me. So what is the maximum speed of the system? 1,005. Some give you 1,005, the rest, the other. What is speed? What is the maximum speed? Yes, class? Okay, lane also 1,005. This one is the maximum speed. This one be the maximum speed. Why? Because why? Because limitation. Remember that, limitation. Okay, this one, yeah. What is the maximum speed for design, for example? For designing a motor, you want to design the motors, you have to design the motor, use the maximum numbers, the big numbers. This one for design purposes. Okay, design what? You want to design the motor, of course, right? Because the system will be run by the motor. Of course, yeah, after you have all the numbers, you need to multiply by safety factor. You cannot just simply take the numbers and ask vendor to come to you and then you buy things. No, you have to multiply with safety vendor. How do you decide safety vendor? How do you decide? DECID. How decide? You have to do SFR. You have to do what we call approximation. Approximation methods. This one is method. I'm not going to talk this one. You'll be doing this one in design class. Okay. So if we can go back to this one. So this example number 5, I slowly browse through the example number 5. Look at the results. Look at the results. Sorry, number 6. Number 5 exactly the same. Number 6. Number 6. If you have notes with you, number 6. What does it say? Determine the maximum speed here. Determine the maximum speeds of the shaft and also speed for design purposes. Okay, so each bearing have 5 kilonewton. Sometimes they provide you both, sometimes provide you one value for both. Yeah? So I'm not going to do this one, the whole thing. I'm going to check out the results. This one, look at here. You have omega y, you have ny. We have this one and also 1003, for example. You do another one, you have x and x with 1008, and then you make decision. You have 1003, 1008. So the maximum speed will be 1003 for what? Safety purposes. Safety. Isn't it? The other one, for design purposes, you look for the bigger one. Okay. Okay. So what is the reason 1003? So my question, what is the reason concrete, concrete reason? What the concrete reason for NX, the maximum speeds? This one in exam last semester I did ask this one. What is the concrete reason that you select NX to be your maximum speed? What? Anyone? As usual, you don't respond, I will leave it like that and you have to answer on your own. And you can seek the answer on your own. You can discuss with your friend. No? No one that answer?
Doctor,
Yes.
is NS or NY?
No, sorry, yeah, sorry. Thank you. Thank you. This one is NY. Thank you. Who's on the line? Lin, correct? Or Tan? NY. So why we select this one? What is the reason, the concrete reason for the NY to be the maximum speeds? Why? Yes, Tan or Lin? Or Lee? Anyone?
Because the bigger force produce NY.
Because of the bigger force. The force is the same, 5 kilonewton for each, isn't it? Correct? The force 5 kilonewton for each bearing. Anyone? Limitation, yes, correct. The limitation. The other one is what? When you're talking about a concrete reason, yeah, you have to say that the bearing Y can run only up to 1,300 RPM. beyond that or exceed that, it will fail or it will giving problem. While the other while the other bearing can withstand up to 1008, which is still what running with the same or steadily, while this guy will be now giving problem. Correct. Why you select this one as your bigger number to be your design purposes? If you design this one is 138, 1003, yeah. So you are what? You are under design, because remember you have the motor also the motor when you want to connect the motor, of course via shaft, there must be a coupling, isn't it? The coupling depreciate these speeds, correct? So you want to ensure that there is not depreciation of speed when the motor run the system. So that is why we have this one. Okay, I think that's about it. I'm going to I'm not saying that our class is end, yeah. I'm saying that that's about it, meaning that I'm going to look for the example here. Don't get me wrong, yeah. Okay, problem number 1. So before that, any question you want to highlight or you want to ask before we move to the problem here? Solution is up to you. Huh? You want to solve it analytical, you want to solve graphical, it's up to you. Okay. I think couple last semester students solved by vector IJK. It's okay. Because as a lecturer we cannot expose to every solution because it's not, we don't have ample of time. If you have leisure time, then you can use with so many solution. Yeah. So we are going to use basically the very normal solution, and most of the books solved by that solution. Yeah. I think last method they use IJK. It's okay. So it's still okay. IJK is what Cartesian coordinates. Okay. Yeah. It doesn't matter. Huh? What does matter that you have to understand every solution, but you have to mastering one, because that method that you mastering has to be your solution in your exam or test. Okay, now let's start with this one. You have now 10 more minutes. I'm going to give you introduction only, yeah, because we run out of time. 9:35. We have to end 9:50, 24 minutes. Yeah. So figure 1 show 3 meters span here, and the maximum and then the speed is sorry, the bearing is A and B, correct? A and B, and you have carry X and Y. This one shaft X and Y. Speed is 500 RPM. Initially, this is totally balanced. So what does it mean now? What do you understand by initially that these are totally balanced? Then after some time, you make modification. Before you make modification, the system are totally balanced. What does it mean? Anyone? MR, yes, correct. Yeah, that's correct. In other words, you have to put in word, yeah, Tan or Lin. In other words, that the radius of rotation of the disc X and Y are fall on the radius of shaft. This one radius, this one fall on the radius of shaft. Okay, so without this one, yeah, without this one, initially there's no modification. So you found that the radius of here of X is equal to the radius of the fall on the radius of gyration. Sorry, it's not gyration, radius of rotation. Okay, so that's why you found that all the M are becoming zero as been mentioned by one of your friends just now. Yeah. Okay. Excuse me. Then you make a modification. Look at here. You make a modification on this X. What you done? You done this one. You add one mass. You add one mass, 1 kg, at the radius of 3 cm, at the position of 90 degrees. This one, yeah, you add one. So if you look at one from one point of view, yeah, to look at this X will be what? This X will be so to make you understand the one, yeah. You have this X now. It become, you add one mass. This one is shaft. Then what happened? Remove mass of 1 kg. radius of 4 at 0 degrees. 0 degrees is here. So 4 is here. So you remove this one will fall here. You make a hole, for example, because we do not know, right? So you make a hole, a part of that. This one is hole. So now the system is not balanced. Okay, the system is not balanced. Same thing for this y. You add 1 kg with the radius of eccentricity, and also you have the position, and you remove mass 1 kg at the radius of rotation and at the position of 180. So the equation now is, for this condition, when these things are no longer balanced, calculate the dynamic force on the bearing A and B. Then the total force of bearing A and B, if this X and Y is 10 kg. This one is nothing. This one is something new to you. The next one is the total maximum force of bearing A and B. This one we already done. This one we haven't done yet because we do know why this one. Yeah, you found that this X 10 kg. This one, what is the difference between 1 kg and 10 kg? I will explain to you this one before we move. Before we start doing the analysis or solution. The total maximum force of bearing A and B, the maximum and minimum vertical force of bearing A and B. So this is a very typical question in your work. Yeah. So now, what is the difference between 1 kg and 10 kg? This one. Anyone? Anyone? What is the difference between this 1 kg, this 1 kg, this 1 kg, and this 10 kg? What is the difference? So this 10 kg is basically this one, the 10 kg, solid one. Then you add another one. It become, if this one is 10 kg, this one is 1 kg, it becomes 11 kg now. 11 kg, correct? But suddenly, you make a hole, or you draw, or you drill it, and you remove a mass here. You remove 1 kg, so minus by 1 kg, it becomes 10 kg. Okay, so this 10 kg, the final one, this one after modification, remember this one, yeah? After modification, to be used, write down in the notes, yeah? To be used in static analysis. Okay, let's assume, because this one is very fortunate, we have 1 kg and 1 kg. Let's assume another example where you found that it is not the same. Look at here. Initially, you have what? 12 kg. Look at here. A 12 kg. Are you still with me, class? So quiet there. Yes. Okay. Look at here. Look at problem number 2. I cannot explain this one because you have 1 kg. You add 1 kg, then you minus 1 kg, so become 10 kg back. Right. So now I'm going to explain another one. So look at here. We have 10 kg 12. So now A for being A kg, correct? Then you remove 2 kg, you minus by 2 kg, right? Then you add 1 kg, then you add 1 kg. It become 14 minus 1 become 13 kg. You understand me? So when you do the static analysis, this one is when you do the static analysis, this one is what is that? One, I have X and Y. I have X and Y. This one is your mass, isn't it? This one is your M. This one your A and B. A and B. So your A now is no longer 12. It becoming 13 times 9.81. You understand me or not? Can you see that one? Yes or no? Is it okay with you with this one, or you want me to draw another one? Never mind, put it there. here, here. This one is Rx and Ry. This one is MA for A. This one is your MB. So here you'll be MA is 13.9.81. Okay, no longer 12. Look at B now. What happened to B? B, what does it tell for B? Initially B is 10 kg. Put it here. If B is 10 kg, on this B add 3 mass plus 3. Then remove 1.5 minus 1.5. So 13 minus 1.5 becoming 1? Anyone? Thank you, 11.5. So you use this one. 11.5 is this one. 11.5 multiplied by 9.1. So remember this one. Static analysis must be used, or must be applied on modification, must be applied after, it's not after what? What's the modification? Dynamic what is on modification mass. What is that? That is basically coming from this one, 2 kg, 1 kg. If you add, equal to positive n. If you remove, equal to negative m. Okay, so that is how you are going to do or to go about it on this solving the problems. Yeah. Let me check whether any other example which is what do you call it, rare or different from others. Yeah. Look at question number 6. Okay, now tell me, question number 6, class. Tell me, what does it mean? Look at the figure 6, show a shaft carry 5 days, A, B, C, D, and E, mass 10 kg, for everyone mass 10 kg, with center of gravity is about its center of rotation. What does it mean? It means what? What does it mean? It means the system is totally balanced. Okay, it means the system is totally balanced. Then only you make modification. Then when the time you make the modification, the system is no longer balanced. Okay, so the rest I think not very difficult. You can do this one on your own. You can start doing this one after I give you the deadline of submitting the deadline of submission of this assignment number 5, I suppose. Yeah, the rest I think is not very difficult. Yeah, this one, okay, here. Inshallah, the next class, yeah, I'm going to solve this one. This one I don't want to solve because when I solve, they will only halfway. So it's very difficult for me to continue the next lecture. So supposing you have this one in such manner, look at here. I make it bigger here. Figure show a system rotating bodies comprises of circular. This L is circular, yeah. A, B, and C, and R, supported by bearing X and Y. The system is initially balanced. Modification are done now. Look at here. The modification is what? This A, removal of 0.1 kg mass at position 90 degrees. So this one, remove negative, put it in negative. B, removal of 0.5 to 70, this one, also removal. The next one, C, is also removal, at 0.1 at 0 degrees. So this is not difficult. This one is not. This is difficult now, isn't it? Because this one, we have the radius is 0.2. This one is a radius. So this one, what will be the radius? What will be the radius one? There is what they provide you, 30 degrees. So what will be the radius? Look at it. The radius will be measured. If I can make it bigger here, so the radius must be measured from this point. This is the center of rotation to that point. So that will be the radius. So it simply means that the radius will be what? The radius is equal to 0.2 plus what? Plus what? 0.2 plus a small portion of this one, isn't it? There is what they provide you, 0.1. So this one is 0.1. So what that is, what will be this one? This is a small portion of this one. You understand me or not? You understand me or not? So the radius will be measured from this one perpendicular to the point that you modify this one. So it's basically 0.1 plus what? Plus 0.1. What? Anyone? Anyone? 0.1. Whatever it is, this one, you take this one.
0.1 sine 30.
Thank you. Yeah, sine. So that will be the radius of A. Okay, this one, most of students do not know how to calculate this one. What they did was, I think I remember this one when I designed this equation. What they did was they calculating this one, which is not correct. They put it here 0.2 square, add up this one, then this one 0.1 square, which is not correct. Must be measured perpendicular to the shaft. Must be measured perpendicular to the shaft. Okay. So I think that's about it at the moment. So when we come back, I see you again in the next lecture, I'm going to do this one completely. Not complete the whole problem. I'm going to pick up one of the problem that might be your reference to do the next one. So then you can use the selected problem to be your reference in solving the problem related to the topics. Okay. So any question before we close our session today, class? Any question?
Doctor, our test one cover until what chapter?
Okay, stay tuned. The next today is Monday, isn't it? Sorry, today is Sunday, right? So on Wednesday, remind me, is it Tan or Lee or Lin? Who's online? Who asking just now?
Doctor.
Teng.
Yeah,
Okay, Eng. Okay, Eng. Remind me on Wednesday. I'm going to, to expose to you or to explain to which topic will be included in your test one. Because the reason is why some, other section do not, finish yet the topic we are decided. So let's say they promise me to complete this Wednesday. So when every section completed, then I will explain and I will talk or discuss what topic until what topic in the test one. Is it okay for you, Eng?
yes. Okay, Doctor.
So
Thank you.
just remind me on Wednesday. Sometimes I'll forget about things. So remind me on Wednesday. Immediately before. Immediately after the class start. See what will be topic in the test. So I'll be explaining about 30 minutes for the topic in test. And together with that, I also provide you the special test. It's not special test, basically it's a mock-up test. I give you during the test time. I give you during the class time. You have to submit after night time. At night time, I give you in the class time, then you submit it at night time. So we have ample of time to do that one. So and that one will be individual assignment. Perhaps you have to set on the previous test. Okay. Okay, class. Thank you. Thank you for everyone staying with me. Thank you for your response. Thank you for having me, and thank you for stay tuned. Respond. Some of you very active in class. Thank you very much. So with that, I end my session with Assalamualaikum warahmatullahi wabarakatuh, and hope to see you again in the next session. Thank you, class.